Hi, everyone. I'm going to present our paper at the International Conference on Software Engineering 2022. The paper is titled with Natural Attack for Portraying Models of Code. I'm Joe Young, a PhD student from Singapore Management University. This is a collaborative work done by Jack, Jinda, and David at SMU. There are many research work has been done to use AI models for solving software engineering tasks, including deep web prediction, bug localization, clone detection, code search, and so on. If we just look into the papers published in the last 2 years, we can find hundreds of papers on these topics. It is very exciting because the programmers' productivity can be greatly boosted, but it is also kind of worrying as the AI models are not robust enough. Researchers have shown that the adding slight changes to the model's inputs can make the model to produce wrong outputs. On the left side, it might be the most famous creature in the adversarial communities. A model can correctly recognize the image as a panda. We can use some very simple method to compute some carefully chosen perturbations. For example, the noise in the left figure is computed by simply following the gradient direction of this model. Then, after adding the tiny perturbations, which is almost imperceptible to human eyes, the model recognizes the image as a gibbon with a very high confidence value. It is not good because it is still a panda, which means the model makes some errors. On the right side is an example from the software engineering paper. The original traffic sign can be correctly classified. However, if we rotate or shift the image a bit, say for one degree, it will be wrongly classified, which may cause serious problems to a self-driving car. We call such modifications to the images as semantic preserving transformation because an image of a panda with noise is still a panda. But such semantic preserving transformations can change the model's output. While the models of code are not robust as well, we understand that there are some other types of semantic preserving transformations on code. For example, converting switch statement to if statements, adding branches that will never be reached. But we focus on identifier renaming as a transformation in this work. It is also worth exploring other types of transformations in the future works. On the example illustrated by the left figure, the original model can be, the original program can be correctly classified by a model, but if the variable is renamed to something else, it may be wrongly recognized by the same model, even though the program behavior should be exactly the same. On the right side, the model can predict its function name. If we change the original variable name, alum, to some other variable names like upper hash digits, the model will predict a totally different label with very high confidence value. The fact that semantic preserving transformations on code can also change the model outputs highlights some security threats to the models of code. A typical threat model is showing us in the slides. Assuming there is an attacker or a malicious programmer in the company, and the company deploys AI models to conduct several software engineering tasks, like detecting the defective code, checking whether a code snippet is copied from somewhere else, or decide the authorship of some code snippets. The attacker wants to cause some negative impacts on the code base, for example, merging bulky code or copy some code from the online repositories with very strict license. Anyway, just negative impacts. To avoid being detected by the model, the attacker uses some semantic preserving transformations without modifying the function of his code to create adversarial examples. The model of code are usually deployed in the server where the attacker cannot access to the white box information like the model parameters. So this paper assumes a black box attack setting. However, software development is still a human in the loop activity. Code review is widely adopted as one of the best practices in many countries and companies. Researchers reported that over 20% of patches in Eclipse and Mozilla projects were rejected because the patches used bad identifier names or violated coding conventions. If we look at the adversarial examples on the left side, changing the variable name, alum, to like upper hash digits or music service is actually not natural. These two new identifiers have their own specific meaning and clearly cannot fit into context. They are very likely to be treated as bad identifier names, and such obviously unnatural adversarial examples might be able to fool the model, but can be rejected by the human. So we suggest that the adversarial examples for model the code should consider two requirements. On the one side, adversarial perturbation should be program semantic preserving. It cannot change the program behavior, so this requirement caters machine as the audience. On the other side, the perturbation should also be natural to human judges, catering human as an audience. We quote one statement from a project in UC Davis. It says that software that's written has two audiences, the machines that run it and the humans who maintain it. This, to some extent, inspires our study. But how can we generate natural perturbations? One promising way is to use the modern pre-trained models. Existing large pre-trained language models have a basic pre-training task like called masked language modeling. Given a text where some tokens are masked out, for example, the token after I have a is masked. We represent it using a special masked token in CodeBERT. The goal of the masked language modeling is to predict the value of the masked tokens. In other words, the model tries to figure out what words are more natural here. Say the results can be I have a job, I have a problem, I have a result. They all seem good. Besides, this masked language prediction function is context aware. If we add additional information to the input, say, I have something which is hard to solve, we feed the new text into CodeBERT and obtain some different results. The prediction results become like problem with a very high probability, followed by a bug, and another problem with the first character being capitalized. The results are also natural, as problem and a bug can be very hard to solve, right? It means that the masked language modeling can predict words that can fit into the context. It's context aware, which means the naturalness. The above examples motivates us to use masked language prediction to generate natural substitutions for identifiers in code snippets. For example, an original identifier is the prop, and the CodeBERT can predict the natural replacement property, which can describe the types of the variable clearly. We can extract all the local variables from a code snippet and generate a list of candidates for each variable using the masked language prediction. But beyond that, we re-rank the candidate list again. We use each candidate to replace the original identifier, so prop, property, and feed them into the CodeBERT. But this time, we compute the embeddings of each token rather than predict the masked tokens. Then we compute the cosine similarity between the original and the new identifiers embedding. Using this cosine similarity, we re-rank the generated candidates and select the top 30 candidates with the highest similarity to generate the adversarial examples in the future steps. Okay, by so far, we have had substitutes, but how can we generate adversarial examples? Do we need to enumerate all the possible combinations of replacements? Maybe not, but we have some basic expectations for a good attack. First, it should be query the model for as few times as possible. As explained earlier, the AI models are usually hosted remotely on the server. Querying a model for so many times can be very suspicious. Besides, we also expect the code snippet to be changed as minimal as possible. If changing one variable can fool the model, then don't change two variables. Otherwise, it's more likely to be found. With two expectations, we propose a two-stage method to generate adversarial examples. The first step is a greedy algorithm to find these examples fast, and the second step is based on genetic algorithm, which is applied to do a more comprehensive search if the former one fails. Let's introduce the greedy method. We first want to know which variable in the code snippet is more important, indicating if we change it, it's more likely to have larger impact. Looking at the code snippet on the left side, assuming that the model's output on the original code snippet is like 0993, and its code snippet has two variables, A and B, and both of them appear twice in the program. For a variable A, we can obtain two variants of the code snippets generated by replacing one of its occurrence with the unknown token, just like this. So we have two. Then we feed the replaced snippets into the model again and see how the confidence score change. The change indicates that if the model knows the real value of this variable, how much confidence it can gain to make a correct prediction. Since a variable can appear for multiple times in a code snippet, we use the sum of all the changes at a different occurrence as the overall importance score of this variable. We can compute the score for each variable and rank them from the highest to the lowest. This corresponds to the third line in the algorithm on the right side. For each variable, we iterate all the candidates for it and generate program variance by substituting the original variable using the candidate. Note that here we need to replace all the occurrence of a variable to ensure that the transformation is semantic preserving. Then we feed the new program into the model, see whether the output label changes. If yes, then we have found an adversarial example successfully and connects it. But if not, we record the program variant and proceed to the next substitute. If we still don't find an example that can change the model output, we just select the one that can reduce the confidence value most, and then replace the next variable in this new program. The process continues until we find a successful adversarial example or all the variables have been iterated. Now we introduce the genetic algorithm to conduct more comprehensive search. We first explain the chromosome representation. Assuming a code snippet has three variables, the solution can be represented as a list consisting of three tuples, representing the original variable and the new variable in the solution. So here it represents a solution that replaces the variable A to IKU, B remain the same, and C becomes a car. We use two simple operators in the genetic algorithm. The mutation operator randomly selects a gene, in other words, the tuple, and randomly selects a substitute from the candidate list. For example, the variable B in the program is selected and replaced with a baby. The crossover operator is applied to two chromosomes. It first randomly selects the position to cut the chromosome, and then swap the first two parts of the chromosome to generate two new chromosomes. The fitness function is also easy. We, as this problem is essentially a combinatorial problem, aiming at maximizing the distance between the victim model's prediction on the adversarial examples and the original program. So we can just use the changes in the confidence score as a fitness function. For example, changing A to X can cause a decrease of like 0.12. Then it is better than changing A to Y, which has a negative fitness function value. Let's briefly explain the workflow of the GA attack. We need to specify some parameters first, like the maximum numbers of iterations, the crossover rate, and the number of generated children in each iteration. We use information from the greedy algorithm to initialize the population. From the greedy algorithm, we choose the chromosome that is closest to the successful attack. For each variable in this solution, GA attack creates a chromosome that only changes this variable to the corresponding substitute, and it keeps other variables unchanged. So in this example, we can, like this one, we can initialize a population of 3 chromosomes. For each of them, just one variable is changed. Then we perform crossover and mutation to generate the children programs. After generating children in one iteration, we merge them to the current population and perform a selection. GA attack always maintain a population of the same size and discuss the chromosomes that have lower fitness function. We evaluated our method on 3 critical tasks and 2 state-of-the-art pre-trained models. The vulnerability prediction task aims to predict whether a given code snippet contains vulnerabilities, the code clone detection, and to check whether 2 given code snippets are cloned, and the authorship attribution is to identify the author of a given code snippet. We obtain the datasets and the pre-trained models from PyroWorks. We fine-tune those pre-trained models on the datasets. The table displays the results of each model on different datasets. The first research question explores whether the naturalness-aware substitution can help produce adversarial examples that are more natural to human judges. To answer this question, we conducted a user study to analyze the naturalness of examples generated by the proposed method we called ALERT. Also, other 2 baselines, MHM and MHNS. So MHM is a prior state-of-the-art black box attack for model decode. It selects substitutes from a large corpus without considering the naturalness. So we also use a modified version to make MHM work for both Java and C programs and select the naturalness-aware substitution, just as the alert did. In total, we sampled 300 code snippets generated by different methods and conduct a user study. The users are given a statement saying the new variable names looks natural and preserve the original meaning. And the participants need to give a score on like 5-point Likert scale to judge the statement. 1 means strongly disagree and 5 means strongly agree. We plot the average score in this figure. The results show that participants consistently find that the adversarial example generated by alert are natural, while those generated by the MHM are unnatural. The second RQ is about how successful and minimal are the generated adversarial examples, how scalable is the generation process. We use 3 metrics to measure the performance of an adversarial example generation method. We have attack success rate, variable change rate means how much like the proportion of variable changed in all the program, and the number of queries to the victim models. We can observe that the simple greedy attack can already outperform the MHM search method, and using the genetic algorithm can boost the results even further. On all the victim models, alert modifies fewer variables. It indicates that alert makes like minimal changes to the input and produce more natural and imperceptible adversarial examples. Besides, alert queries models for less times than MHM and NF does, showing that our model is more scalable. In this research question, we explore the effectiveness of using adversarial fine-tuning as a defense against attack. We leverage our method to generate adversarial examples for each victim model and on their corresponding training set. These generated examples are then augmented into the original training set and form a new one. We call it adversarial training set. We then fine-tune the victim models on the adversarial training set. So from this table, we can observe like all the adversarial fine-tuned models perform much better than the original ones. The adversarial improvement, the average improvement on the examples generated by solely using the greedy attack and employing the GA attack is actually close. So we suggest that using greedy attack for adversarial fine-tuning, which is faster. In general, the adversarial examples generated by our method are valuable in improving the robustness of victim models. Let's conclude the paper. In this paper, we highlight the naturalness requirements in attacking models of code. And we show that models fine-tuned on state-of-the-art pre-trained models are vulnerable to our attack. Adversarial fine-tuning victim models with these generated examples can improve the robustness of the CodeBuild and the GraphCode models. In the future, we plan to extend the attack to other models and transformations. We also plan to develop robust pre-trained models rather than gain robustness by fine-tuning again and again. That's the presentation. Hope it inspires. Any inputs are welcome and helpful.